And we'll start out with the modified Rodrigues parameters. What we started up last time was shadow sets. So, Spencer, what is an MRP shadow set? Sorry, different Spencer. I had two Spencers in a row. That was bad seating, guy. That's really your fault. That's not on me this time. Sorry, I meant the guy behind you. Right. Does it have to be the long rotation?
No, it's just the opposite set from the one.
It's typically, practically it ends up being the long because we want the other set. It's just the alternate set, and it's one way to describe it. And the name shadow set, when we develop that stuff, it's kind of, you've seen the singular behavior wherein we have near zero behavior. One set is extremely well behaved. It's kind of like having the light shine straight down on an object, right? And the shadow's right there, and you move a little bit, and you get a nice little behavior. But then when you go 360, the light comes off to the side, the thing goes off to infinity. The other set has completely the opposite behavior. The 360 is the really well-behaved one, and the 0 is the one that kind of gets driven off to infinity, right? So that's what these shadow sets are. It's just the alternate set of MRPs. And that nomenclature you'll find a lot with MRPs. You could apply it with quaternions, but people won't know what you mean when you say a shadow set quaternion. They just talk about the alternate quaternion or something. So, okay, so the shadow set. Anybody remember the mathematical mapping? Quaternions, we just reverse sign. But with MRPs, Jordan?
Reverse sign and divide by the magnitude.
Magnitude squared.
Oh, yeah, sorry.
Sigma squared, right? So at which point do we typically choose to switch from one set to another? Marielle?
A little after 180 or?
180. So what is the MRP at 180? What was the trick, the trigger we have in the code that we check for? Is it Brett? No. Ben. Equal to 1. The norm is equal to 1, right? So we draw this surface, that's this norm equal to 1 surface, but now in this case in MRPs, this is not a constraint surface, this is just a surface in three-dimensional space that illustrates if your MRP coordinates go through the surface, you're now describing the long rotation. And that's precisely when we want to do it. So if it's equal to 1, and Jordan said it's minus sigma over the norm squared, and the norm is 1, it's really just minus a set. Is that what, is it Daniel? Yes.
David.
David, so is that what you would put in code? If it's equal to 1, then just do minus sigma?
No, because you might step over that point, so you don't have a range.
Sometimes people look at these things and again, they think of it almost as a constraint. Oh, it's horrible if I go past 180. No. The math is really well defined. In fact, there's papers that talk about going past to 200 or 300, or maybe you have a longer range that you're okay with tumbling, You can do that. Nothing bad happens. So in the integration, just do your normal stuff. Nothing crazy has to go on. It's just after you finished your time loop, then check. If the norm is bigger, divide by, minus divide by the norm squared. That's it. And then you stay to within mathematical precision. You don't lose anything. Everything's cool. Okay? So in analysis, we often have just, hey, this is equal to 1 precisely. In the code, there's no need to iterate in your time step and hit that surface perfectly, so you can just do a little simpler math. Just step through it and do the full math, and it's easy. Okay, so that was that. Let's talk about the differential. Let's talk about adding, subtracting. Anything special, we know we can do it through DCMs. Was there anything special about adding, subtracting with MRPs that we should remember? Go ahead.
Negative is the opposite rotation.
Right. Same thing with CRPs. We had that there as well. So that's really handy. So if I have to, if I have one attitude from body to, from inertial to reference, and now I have to subtract the one from the reference to body, instead of adding minus 30, you can also subtract plus 30, right? Basically. So in 1D rotation, this is really simple. In 3D, not necessarily. But with CRPs and MRPs, the attitude of B to N is simply minus that description from N to B. So that means the addition formula we had, we could actually use addition for both addition and subtraction. Just instead of adding plus 30, you just reverse the MRPs and give minus that sigma from that next rotation. So one formula can handle both cases. If we do the direct addition property, where we didn't go to DCMs, but we used the MRP math explicitly, were there any issues we had to worry about? Kaylee?
When your principal rotation angle is equal.
Exactly. Because you can add or you can subtract two rotations, depending on which formulas you're using, where the net result is a 360 rotation, which of course is the same as a 0 rotation. And in the code, you can easily avoid that by just checking the determinant. If that thing is reasonably close to 0, all you have to do is switch one of the two to the alternate set. And now instead of adding up 180 and 180, giving you 360, you're adding up 180 and minus 180, which is the same orientation, and that gives you back 0. So there's little tricks you can do and come up with very fast, non-singular ways to do addition subtraction. Good. Moving right along. The other thing we have to do is differential kinematic equations. So we have the sigma dots equal to 1 over 4. Let me just write that one out instead of waving in the air. Sigma dot equal to 1 over 4 B of sigma times omega, right? And if you want to be explicit, these are all these kind of things. Okay. That's horrible handwriting, even for me. There we go. Anything special about this B matrix? GK.
It's almost orthogonal, but
Okay.
multiplied by a constant.
Right. So this matrix, if you did B times B transpose, we get identity times something, essentially, right? So it's not quite orthogonal, but that's something. This makes it so much easier. Again, there's different works we've done in the past where we have to analytically deal with the inverses of these B's, and so that the inverse of this is simply the transpose multiplied times a scalar, saves you pages and pages of algebra. It's a very convenient form. So good, we did have that. So that's kind of similar to the quaternion. There was that buffered 4x4 form that was truly orthogonal. This one isn't quite orthogonal, but it's pretty darn close, which is also still very convenient. So it's a nice feature of these things. Good. Then, let's see, we ended up talking about symmetric stereographic orientation parameters. What makes them symmetric? Thibault, where does that name come from? There's asymmetric and symmetric sets, so we reviewed them at the beginning. So with these, the symmetric stereographic orientation parameters, it's a superfamily of coordinates. There's in fact infinity instances of it. And they contain the CRPs and the MRPs.